Hello, my name is Yuren Kong, and I'm a PhD student at the Institute for Information Processing at Leibniz University Hannover. Now I'm going to present our paper, NODIS, Neuroordinary Differentials in Understanding. Our paper investigates the problem of scene graph generation. Scene graph is a representation for semantic image understanding. The nodes indicates the objects whereas the edges show the relationships. In order to generate a scene graph, we need to localize the objects, label them, and infer their relations. The applications of scene graph range from image retrieval to high-level vision tasks, such as visual question answering, image caption, and visual answering. The previous works mainly contributed to three aspects: context information extraction, loss function, and learning method. For example, graph RCN use graphical models, whereas neural motifs introduce the recurrent neural networks to achieve contextual message. In RealDN, graphical contrastive losses are designed. Meanwhile, GPSNet proposes a node priority sensitive loss inspired by focal loss to reduce width of well-classified objects. On the other hand, scene graph prediction with limited labels introduced a semi-supervised method that assigns probabilistic relation labels to unlabeled images. In our paper, we used the neuroordinary differential equations, which are continuous and can be interpreted as a deep residual model for scene understanding. Unlike most state-of-the-art algorithms, we regard the object classification and relationship inference as integer linear programming. Assume a set of nodes be paired, where the nodes represent all possible subject-object pairs. Each node is assigned to a predicate label k, which is associated with the score alpha. The integer variables x indicate if the node B is given label k. The number of labels per node is limited by Tv and the total number of labels by k. We also include a term beta, which models statistical prior knowledge about co-occurrences of object pairs V with V'. Then we can get the ILP for relationship classification, where omega pred is a scalar weight. The power of end-to-end learning has been demonstrated. However, it is not possible to backpropagate through ILPs. Inspired by flow optimization, let alpha t be a function in time that assigns continuous scalar weights which express label strengths, and beta t be a function assigning scalar weights according to co-occurrence. The optimization problems of ILP correspond to ordinary differential equation models. Since it is hard to explicitly define alpha t and beta t, we use neuroordinary differential equations to parameterize ft by a function f theta t based on neural network with parameters theta. We propose NODIS by means of neuroordinary differential equations that can learn end-to-end to perform the same task as ILP. Our model is built on faster RCN, which provides proposal boxes, feature maps, and object distribution. There are two fundamental modules: object classifier and predicate classifier. Each of them contains a neuroordinary differential equation layer, OODE and PODE. For both of them, we use bidirectional LSTMs as the approximate function in the ODE solver. In the object classifier, the feature maps, position information, and object distribution from faster RCN are used. The object class courses are computed by the OODE and the following linear layer. The input of the predicate classifier are semantic information from the object classifier, feature maps of objects and their unibox, and spatial masks. The visual vectors and semantic vectors can be preprocessed by fully connection layer, GraphCNN, or LSTM. The final class courses of the relations are computed by the PODE followed by two linear layers. We validated our method on the visual genome dataset for the task of scene graph generation. For fair comparison, we adopted the data split from Xu, which is the most widely used. The training set has about 75,000 images, while the test set has about 32,000 images. According to the data preprocessing strategy, the most frequent 150 object categories and 50 predicate types are selected. There are 3 standard experiment settings in order to evaluate the performance. Predicate classification predicts relation labels when ground truth bounding boxes and object classes are given. For scene graph classification, ground truth bounding boxes are given. The model predicts object label and relations. For scene graph generation, the input is only the image. The most widely adopted recall metrics for relations are used to evaluate the system performance. To provide an intuitive interpretation of the time in the ODE solver, we use a model trained with the hyperparameter Tn equal to 1.5 and evaluate using different latent vectors corresponding to different points between 0 and 2.5. The hidden states at 2 and 2.5 imply extrapolation. The features are more and more refined by the neural ODE layers if time increases. Hence, more objects and relations are correctly classified. After 1.5, increasingly many relations are misclassified due to the extrapolation. Our results are shown in the table. The bottom part shows results of the proposed ODE layers using 3 different front-end, respectively fully connection layer, GraphCN, and LSTM. They bring the different representations for the ODE layer. As can be seen from the table, most recent methods such as MotiveNet, VC-tree, and CMAT, including ours, are very similar in performance with respect to the sources in SGGN and PredCRS. The only exception among state-of-the-art works is GCL in 2 out of 9 sources, but their object detector has different parameters. For SGCRS, however, our proposed model turns out to be very effective. Both our FC and our LSTM perform very similar. Their sources improve state-of-the-art about 2%. Here are some qualitative results for scene graph generation. The purple color indicates correctly detected objects and relationships, whereas orange means failure. The blue color indicates false negatives. That means relations are not annotated in the ground truth. Sometimes a few false positives are semantically meaningful. In conclusion, we present neural ordinary differential equations for scene understanding. The idea of this work is based on the fact that integer linear programs can be used to solve problems defined by ODEs. Therefore, we can find a system of ODEs that can produce the solution of ILP. Since it is impossible to manually define the ODE system, we can use a trainable function approximator instead of an explicitly defined system. We use this newly defined module for object classification and relationship classification. The proposed model using ODE layers shows large improvements on SGCRS, between 2% and 3% compared with the best SOTA in that category. We believe that ODE layer can be a valuable improvement for neural architectures in semantic image understanding. Code and trained models are available on GitHub.